The purpose of this video is to make some graphs of transformed sine and cosine functions, what you might call sinusoidal curves, because a lot of them are based on the sine curve. So we're making the assumption here that you have a basic knowledge of what the graph of the sine function looks like in using radians for the angles, and understanding what values within the function, what sort of transformational effects they will have on the graph. If you haven't gotten quite that far and you don't have a full grasp of that, you might want to go back and watch a video, or read up on the basic graph, or what the values, what effect the values might have on the graph. So as we get into this example, the important characteristics of the graph of a sine or cosine function are its period, amplitude, the axis of the wave, the phase shift, and then is there anything else to worry about? Once in a while you got to check for some other items that might be within there. So the period would be affected by a horizontal dilation. And if there was going to be a horizontal dilation, there would be a coefficient on x other than 1. And since we don't see a coefficient on x other than 1, we know that the period of this graph will be at 2 pi. That means if I graph a piece of this function that is 2 pi units long, no matter where I start or where I stop, I'll get the whole entire shape of the graph, and then I can just continue the pattern and repeat it. The amplitude of the graph is, remember, that's going to be half of the height of the graph, and that is going to be a vertical dilation. And if we have a vertical dilation, that would be the coefficient in front of the function. We'd be multiplying the output by something. And in this case, we do see a vertical dilation. We see a -2 out in front. And the amplitude of the wave, its formula is the absolute value of b. So in this case, it's going to be 2. So the graph of this graph is going to have an amplitude of 2. Now that's half of its height. So the graph will have a total height of 2. The axis of the wave will be affected by a vertical translation. Let me spell that right there. Vertical translation. And that would be indicated by a value that is added or subtracted to the entire function. And we don't seem to have one, so the axis of the wave will stay at y = 0, or the x-axis, for where the typical sine function is. Phase shift. The phase shift would be a horizontal translation. And that would be indicated by a value that is added or subtracted to our input, added or subtracted to x. And we don't seem to have one there. So we don't have a phase shift. I'm just going to write none here. Is there anything else in this graph that we haven't taken care of? And actually, in this case, there is. We have a negative out in front of that coefficient of 2 that we have not addressed yet. So what is that going to mean? Well, that's going to give us, the negative is going to give us a reflection over the x-axis. So now we know that we have the important characteristics of our graph. We're going to have a period of 2 pi with no phase shift. That's all our horizontals. The axis of the wave, that horizontal midline of the wave, is going to be the x-axis, but with an amplitude of 2 and a reflection over the x-axis. So I might think to myself, if I wanted to just really quickly rough sketch it out, that the sine function typically looks like that from 0 to 2 pi. I do not have a horizontal dilation. I don't have a horizontal translation. I do, however, need to stretch this, so the graph from here would get taller and deeper there as well. But then we're also going to have to apply a reflection over the x-axis. So at the end, my graph is going to look how that purple dashed line looks. But I need to go ahead and work with that in a little more detail and to have a nice graph. When I make my graphs, I ask my students to make their graphs, we just really focus on the maximums, the minimums, and the zeros. So we're going to use these points as our starting points. This is the graph of y equals sine x untransformed. We have the point 0, 0. Sine of 0 radians is 0. We have the point pi over 2 comma 1. Sine of pi over 2 radians is 1. We have the point pi comma 0. Sine of pi radians is 0. We have 3 pi over 2 comma negative 1. Sine of 3 pi over 2 is negative 1. And then we have the point 2 pi comma 0. Sine of 2 pi is 0. Remember that 2 pi radians is coterminal with 0 radians. So they're going to have the same trig function output. So these 5 points that make up the maximums, the minimums, and the zeros of the parent function sine function are going to be the points that I am going to want to use to make my graph. Now, in this particular case, if we look at the full screen here, we were asked to graph the function, but we weren't asked to graph the function on any particular interval. So I guess we can choose our own interval. Sometimes you will be told the interval to work from. Why don't we go ahead and graph this from negative pi to 3 pi, just to look at a little bit of a larger segment and see how this would work. All right, so I'm going to flip the screen, and I'm going to get myself a grid here. And draw some axes. And you can do the same. You might need to pause the video. It might take you a moment longer to draw yours than mine. I think I'm going to lock this in place so it doesn't slide around on me. All right. So maybe we'll do something like this and here. So we're going to go from negative pi to 3 pi. So I'm going to set up a scale where I can use my quadrantals. If I go back to my parent function, I see that if I think about a starting point and an ending point, this 0 is halfway in between. This max is a quarter of the way through the period, and this minimum is 3/4 of the way, if I think of splitting this into quarters. So I might set up my axes in such a way that having quarters is going to be something fairly easy to do. So I might set this up so I have 1, 2, 3, 4, 5, 6, 7, 8. Well, that's just going to get me. I'll go 1, 2, 3, 4. I'll make this pi. 1, 2, 3, 4, 2 pi. 1, 2, 3, 4, 3 pi, and 1, 2, 3, 4, negative pi. So I've kind of scaled this out nicely. I know with the amplitude change, I'm stretching my graph by a factor of 2. So my maximum, which was previously at 1, will become a maximum of 2, and my minimum of negative 1 will become a minimum of negative 2. So I should scale this in such a way that I have room to do that. So I might do something like 1 and a 2 there, a little off. Negative 1, negative 2. So I have that. So now it's time to plot points. Hopefully you have those. I'm not going to flip back and forth to the screen. But on the parent function, I have the point 0, 0. If I want to take this point 0, 0 and vertically stretch it, it doesn't go anywhere. And I want to reflect it over the x-axis. It doesn't go anywhere. It stays at 0, 0. On the parent function, the maximum was at pi over 2 comma 1. It needs a vertical stretch by a factor of 2, and then a reflection, which would bring it down to pi over 2 comma negative 2. The parent function has a 0 at pi comma 0. If I have that point pi comma 0 and I stretch it, it actually doesn't go anywhere. And if I reflect it, it doesn't actually go anywhere. The parent function would have a point at 3 pi over 2 comma negative 1. That point would vertically get stretched and then reflected to 3 pi over 2 comma 2. Ooh, I shifted there a little bit. And then the end of the first period would be 0.2 comma 0. The vertical reflection and the vertical stretch do not have an effect on that. And this would give me 1 period's worth of graph. I've graphed from 0 to 2 pi, and we decided to graph it from negative 2 pi to 3 pi. So I can simply follow the pattern. I went from a 0 to a minimum, to a 0, to a maximum, to a 0. So that will be followed up by a minimum, and then another 0. And working backwards, I would go from a 0 to a minimum, to a 0, to a maximum, and then another 0. And if I connect this with a smooth curve, we have here the graph of y equals negative 2 sine of x on the interval from negative pi to 3 pi. This was just one example. Just look for other videos with other examples that might have some phase shifts and other ones. I hope you found it helpful and just a good basic start. This was not meant to be the end-all be-all, but just one example. Thank you.